introduce our speaker today. We are joined by Niloofar Kamyab. Niloofar is the applications manager at COMSOL, and she specializes in electrochemistry, including batteries and fuel cells. Niloofar received her Ph.D. in chemical engineering from the University of South Carolina, where her research focused on the mathematical modeling of battery systems. And with that, I'd love to hand over to the stage to Niloofar. Oh, Niloofar, you'll want to unmute so we can hear you.
Okay, perfect.
Perfect.
Michael, thank you so much. Can you, before I get started, could you confirm that you can see my slides?
Everything looks beautiful. Yes.
Perfect. Thank you so much, Michael, for your kind introduction. And hello, everyone. Welcome to Battery Modeling with COMSOL. Thank you so much for attending. If you're here today, you fall into one of these categories. You either have used COMSOL or similar tools, so you are already familiar with modeling and simulation, or in the battery world and industry, you're more on manufacturing and experimentation side. Whichever group you belong to, this presentation is all about expanding what is possible instead of thinking of simulation as just separate from experimentation. We want to see how these two could be complementary. What if I tell you that instead of waiting for weeks or days to build virtual battery prototypes and doing characterization to get a sense of how the battery behaves, you can build a virtual prototypes and get to see how the battery behaves under different conditions, and then go back to those experiments and modify those experiments and modify manufacturing process that you're already doing. That's the power of battery modeling. And by learning this skill, you will be unlocking all the benefits for your own work. I really hope that by end of this presentation, you get an overview of what these benefits are, and you see how you can actually integrate and introduce these benefits into your own workflow. What I plan to do with this introduction, I plan to discuss what COMSOL brings to the table, what different functionalities and features are that COMSOL provides you with and enables you to reap those benefits. And of course, at the end, I plan to do a quick demo, show you COMSOL user interface so that you get an exposure to COMSOL workflow and see how you would actually interact with COMSOL and how you would set up a model in COMSOL. Michael already mentioned that in the beginning, but if you have any question during my presentation, if there is any specific part that you would like me to elaborate on, or if you have any specific question in your mind, please put it in a chat. Me and Michael will get to this question at the end. But before I get to features and functionalities provided by COMSOL, we need to kick off this discussion, battery modeling discussion, with a very important aspect, and that aspect is multi-scale aspect of it. We get to other aspects. We get to multiphysics. We get to a diverse chemistry that can be handled, or different aspects and objectives that can be tackled in a minute. But before we get into that, we need to decide. We need to decide what scale fits our project, and what are, first of all, what skills are available and what skills is suitable for our modeling project. What we see on this slide, we see different scales. We see microscales, we see cell scales, and we see package scales. So we want to get a detailed analysis of structural details of all the components we have in our cells, or we want to zoom out a little bit, look at the cell. What we see on the slide is a pouch cell, but can be any type of the cell, and see how the cell behaves under different conditions, responds to different variations in material properties or geometric dimensions. Or we group number of cells together and form battery packs and modules that eventually sits in this case, electric vehicle, and gets integrated with other components that we have in electric vehicle. If you're not in automotive industry, though, this is skills, and this multi-scale analysis is not as specific to automotive. In fact, you can replace the image of this car and have whatever other application you have on this slide, because the idea remains the same, that we have different skills, we can conduct modeling across different skills, And then eventually we can design batteries for a variety of applications. These days, batteries are used in various applications and they all have different requirements and needs. So eventually you need to design a battery that suits, for instance, for electric vehicle or for aviation or for consumer electronics, whatever application you deal with. But that's one thing that you need to have to set the context, and that determines the modeling trajectory that you have. What scale suits your project? Where you should start, or maybe you would like to consider all of these skills. But to answer that question, that what scale suits your project, what scales fits whatever you have in mind, you need to know what type of analysis you will be able to conduct if you go with whatever of these skills that you pick. And what do I mean by that? I elaborate on it. So now we see each scale and we see different types of analysis that can be done. In a micro scale, as you can see, we are looking at, in this case, a porous electrode of a lithium ion battery. We have NMC and we have graphite on the other side. And we get to resolve all the, first of all, structural detail, morphology of the porous electrode, exactly the heterogeneities of the porous electrode, how much of it is binder, how much of it is a porous matrix, and what exactly takes place as you start charging and discharging a full detail and full resolution. Lithium ions, they shuttle from the negative side, go to the cathode, sits inside the porous electrode, and then you flip the sign, and then they exit the porous electrode, go to the other side, and that's just shuttling back and forth of lithium ions between two electrodes. You get to resolve exactly what is taking place, how it's taking place, and exactly the structural details of porous electrode, how it impacts that. Let's say you're a battery OEM, and then you would like to design a battery, a perfect battery. You want to find the bottlenecks. You want to know exactly how you would approach electrode manufacturing in a way that you get to design a battery that doesn't have a bottleneck and in fact performs in an optimal way. Or let's say you're a battery user, you should not necessarily a battery OEM and battery maker to go with that scale, but you will like to, you're using a battery, but you will like to know exactly why batteries exhibiting a behavior that you are seeing under different experimental conditions. So you have some imaging data, you have some tomography data of your battery that you have manufactured or purchased from a battery OEM, and you would be able to conduct such microscale analysis. It's an in-depth analysis. You get to see all the structural details and you get to see all the nuances of the physical phenomena happening in different components. Then we go to the cell level. We are looking at the image in the middle. We are looking at the prismatic cell, but could be any type of cell. Can be pouch like the one that we had in the previous one, can be cylindrical one, can be a coin cell. But now we are zooming out. Still, we have different components of the cell, but our objective is more focused on different material properties. For instance, I mentioned NMC. What if I replace that with NCA? What if I replace it with LFP? What if very trendy these days, I have a blend composite material. I have NMC and I have LFP. What if I change the dimension? What if I change the dimension or the placement of tabs, not just the battery cell components? How does the battery cell respond to that? What kind of performance that I get? Again, back to that virtual prototype that I brought up, and I'm going to bring it up over and over as we go through this presentation. You get to see, instead of going into the lab or going to the manufacturing site and actually building such a cell, you get to experiment with different conditions. You get to experiment with different material properties. You get to experiment with different variations in cell dimensions and get a response before actually committing to building something and testing something. And on the package scales, now we are grouping number of cells together. Here we are looking at a group of, this example is actually 500 prismatic cell for battery energy storage system. And in these cases, typically we are not only interested in the performance of the batteries, but also how we are taking care of, for instance, cooling of these batteries. Then thermal management comes into the play. Whatever form of thermal management we have picked. Here we are interlaying different cooling plates. We have pipes that carry the coolants, distribute the coolants throughout the entire battery pack. And we get to see, are we doing a good job in terms of mitigating all the heat generation? out of the cell, how effective we are doing heat generation, and then how we can go about and designing a perfect heat generation or heat thermal management strategy. We will revisit this thermal management later in this presentation because I want to elaborate on the importance of thermal management. But you see the point that on the package scales, typically the objective or our focus is not just batteries, but also all the components that sit within this system that we have. In this case, could be bus bars, could be electrical connections we have, could be all the other components that we have that are actually connected to the batteries and complete the performance. So you see that we can go from a very elaborate to all the way to package scales that we zoom out and we look at all the other components we have. So this kind of translates into different frameworks and model types we have. So if someone tells you that they are doing battery modeling, they need to be elaborate on the scale that they are focused on. Is it a microscale? Is it a cell scale? Or is it a package scale? And they need to elaborate on the framework that they are using because that completely reflects that fidelity or that complexity level that they are resolving. We are dealing with a range when it comes to battery models. And the frameworks that you see on the slide, you have heard of this slide in the battery literature, in the battery community, and outside of COMSOL. Heterogeneous models that, again, you capture all the physics happening inside of your battery. Homogeneous model, they're also known to be as Newman or DFN framework. These are the names or P2D that you have heard in the community. One is scaled down, they are single particle or single particle with electrolyte. And then one is scaled down, we are actually reducing the complexity. We are taking the physics out. We are making the model simpler, and we go all the way to equivalent circuit model and lumps models. All of these frameworks, well-established frameworks within battery community, they are behind the scene of physics interfaces and comps. So they have been already defined and embedded behind the physics interfaces and COMSOL. So two things that I want to mention is that if you have already heard of this framework, just letting you know that these frameworks are already defined. And the second thing, this goes hand in hand with the multi-scale that I was discussing, is that because again, you see that complexity range. It's your decision. Would you like to resolve all the physical phenomena happening inside of your cell? Then you can go with elaborate models like heterogeneous model or high fidelity homogeneous model. Or no, you're a battery pack designer that all you care about is just getting an electrochemical response of your cell. You want to know how the cell responds in terms of voltage, state of charge, and how much heat generates. Then you don't need to go with elaborate models. You can actually leverage simplicity of models like equivalent circuit model and lumps model and couple that with other physics that I will get into in a minute. So you see, this kind of completes my discussion on multi-scale. You need to decide what you want to do. What would you like to get out of this model? Does it requires you to go with a more high fidelity models and involve and a detailed model, or you can go with more simpler model. You can actually use simpler model for one project and more detailed model for another project. It's up to you. All of these options are available in COMS. Now that we got the multi-scale out of the way, now we get to governing physics. At the end of the day, COMSOL is a physics-based package, works on first principle rules. That means all the governing equations, not just for batteries, for any chemistry already, for any physics are already defined and embedded behind the scenes. And when it comes to battery models, when it comes to physics, we are talking about kinetics, we are talking about thermodynamics, and we are talking about mass transport. These go hand in hand. It's impossible to separate kinetics from transport from thermodynamics. They need to be resolved. So when it comes to battery modeling, by nature, you're dealing with a multi-physics problem. Even before we get to flow, before we get to integration with heat transfer, before we get to integration with the structural integrity of your cell, we are dealing with a multi-physics problem. And that makes a COMSOL a perfect tool for such analysis because by nature has been designed for multi-physics problem. All of this physics, they've been already defined. If you're familiar with the field, you're already familiar with different kinetics models such as Butler-Walmer, different thermodynamics model, different mass transfer with different fidelity, diluted solution, concentrated solution, they have been already defined. And as for the extra physics, such as heat generation, for that, easily those can sit within your model and be coupled with the underlying electrochemistry of your model. In many cases, you don't need to do any equation. All these equations have been already defined. But one thing that we really take pride in is the customizability. Is that, let's say, if you want to add on anything, build upon a theory, you can easily go ahead and build upon the existing frameworks and the existing equations that we have. Now that we know what physics are being solved behind the scenes, we know the frameworks, we know the physics, let's get into chemistries. We get to lithium ion battery in a minute, of course, dominant player, then many of you guys might be working with this chemistry. But before a lithium ion batteries, chemistries such as lead acid, old nickel metal hydride, or nickel cadmium, that they were in the market before lithium ion took the place and dominated the market, those chemistries can also be modeled in COMSOL. And lead acid battery, for instance, has its own interface in COMSOL. Lithium ion batteries, if you explore our website, we have an application gallery full of model examples. You notice that many of those examples are actually on lithium ion battery. We have very good reasons for that. The entire community, the entire battery world, it has very good reasons to be concerned about lithium ion batteries. Still, they are dominating most of the applications, and we want to know how they behave, what they behave, and if we can actually push the limit in terms of limitations they have. And also generic batteries, that means you're not limited to lithium ion batteries. I will get into in a minute in the next slide, but the batteries beyond lithium ion. The battery community has started thinking about, well, the limitation of lithium ion batteries, we do our best to find a bottleneck, but what if we can't? What if we have reached that limitation, the intrinsic limitation of lithium ion batteries? Then we need to think of alternatives. And that's when next generation batteries come into play. And I will elaborate on it as well. And flow batteries, that again, they've been around for a while before lithium ion batteries, and for so many applications such as stationary application, they still are very perfect alternative. And you will see again that multiphysics, because flow battery, the name already suggests that flow is part of the operation. They also can be easily modeled by COMSOL. I want to elaborate on that next generation battery that I touched on, because again, if you go to our website, you will see there are a lot of lithium ion battery examples. And we get this question over and over again. What about next generation chemistries? What about the chemistries that are not lithium ion and are currently being explored and currently being studied? Can we also model them as well? Well, the answer is absolutely yes. And I start with solid state batteries, that whether or not you work with solid state batteries, you have heard of it, because these are one of the main, they're introduced to be one of the potential competitors of lithium ion batteries in the future. And we already know that, well, as they're very promising when it comes to energy density, but they have some intrinsic issues that a battery community or people active in the field, they are hoping to resolve. What we are looking at are the results from solid state batteries that is concerned about the connectivity of the electrolyte. That's one of the aspects that people working in solid state batteries are actively trying to resolve and trying to see how they can come up with more electrolyte with a higher connectivities. And you see the effect of connectivity on the voltage curve as you're improving the connectivity, how the cell performance exhibits in the cell voltage. Or people, they already know in solid state batteries that has very poor interface performance, so they might actually go with a full heterogeneous models, because they want to know the binder connection and the contact between the binder and the solid electrolyte, how it behaves, if it leads to any stress and a strain, and if this is stress and a strain adversely affects the cell performance. So they build the heterogeneous models to know how their solid state battery that they're working on actually behaves under different conditions, or if they can rectify the existing issues they have. Moving on to the other example that I want to review with you guys, it's sodium ion batteries. Although not so promising on energy density, But we already know some major battery makers, they have already made sodium ion one of their established battery technologies. So now you get to resolve the battery sodium ion, and you get to see that already the energy density, you see that it's lower, but you can build a high fidelity sodium ion battery and get to resolve the issues that is associated with sodium ion. Again, different chemistries, they have all their own challenges, like lithium ion battery, that intrinsic energy density or that safety aspects that has, or solid state, that interfacial limitation interfacial, or the electrolyte connectivity, or its sodium ion, the energy density, or the diffusivity through the particles. These are all the issues that by building a model, not only you can find the bottlenecks, but you can also resolve the issue. So not only you get to see what issues you have, but you get to see why is an issue and how you get to resolve such an issue. And in sodium ion battery, let's say your objective is you want to build a sodium ion battery that you can push that limit, and you can find a bottleneck in terms of energy density and come up with a recipe that behaves better and comes closer to the performance of lithium ion batteries. Or you go with a complex lithium sulfur battery with a promising energy density that it operates a little bit different from lithium ion battery, because it's not intercalation based, it's a conversion type of porous electrode. But we already know it starts with a very high energy density, but soon, because of some shuttling of polysulfides, it leads to drastic capacity loss, and this lithium sulfur cell has very serious cyclability issues. But let's say you're working on lithium sulfur cell, and we already know how complex a lithium sulfur cell is in terms of operation. Many people that they work with this chemistry, they don't know exactly how this cell operates behind the scenes or inside of the cell. By building that virtual operation, you get an understanding how this lithium sulfur operates in terms of charge and discharge. And then later you get into, once you're resolving all the charge transfer reactions, all the transport of polysulfides involved, you get to see, for instance, the rate of charge rate on it. And as you increase the rate on chargeability of it, or increasing on the rate, exactly you can pinpoint the issue that these cells have. And hopefully you can design a lithium sulfur with reducing the cycling issue they have, or drastic capacity loss they have. Or in other cells, you get to see the concentration of polysulfide across the cell. This is not a type of information that you can even extract out of any type of experiments you have. It's kind of impossible to know exactly, no matter how non-destructive your experiment it is, to know exactly at any point of your cell how much polysulfide exists, because that's exactly the how you can find the root cause of shuttling. You get to see where polysulfides are and why they travel to the other side and participate in parasitic reactions. So not only you get to see the bottlenecks, but that later can help you manufacture better or experiment better, but you get to see things that are experimentally impossible to measure, but then can later shed light on the issues that your cell is exhibiting. Moving on to another chemistry as an example, lithium air. If you have not heard of it, the chemistry is known to be too good to be true in terms of capacity. It's a combination of porous electrode, but air, and a combination of, I always see it as a battery and fuel cell, because air is kind of being fitting into your system, and oxygen concentration affects exactly the performance of your cell. Then you get to resolve the concentration variation of oxygen, and you see how it actually affects the performance of lithium air batteries. And again, the chemistry that it's known to be too good to be true, because it has, again, some electrode utilization issues. You get to dig deeper. You get to vary the oxygen flow rate that you are fitting into your battery and see how it affects the battery. Is it sensitive? Is it not? Or what variations, what changes you need to make to rectify these issues. And that, last but not least, I already touched on flow batteries, perfect for stationary application. We are looking for, not limited to, of course, but vanadium one, that many chemistries are inspired by this vanadium redox flow battery, if not exactly vanadium redox battery. But you get to resolve the flow compartment, how flow talks to electrochemistry and affects electrochemistry. And you get that holistic image of multiphysics problem that not only electrochemistry, but flow compartments, in terms of if you have ion exchange membrane, if you have regular membrane, membrane, if you have different compartments in your flow battery, how you would your cell reacts to it. I review some examples in addition, of course, to lithium ion, because if you go to our website, there are plenty of lithium ion examples that we have, but not limited to that. My point is not that you're not limited to these battery chemistries. So many times we get to talk with so many prospects that they're working a completely novel, that maybe they're not sodium ion solid state or lithium sulfur that are known to be the most well-known next generation batteries, but they're completely working with a novel thing that I really need to ask them, walk me through how the cell operates, walk me through the governing equations or the reactions that are taking place. The takeaway here is that you can work with any novel chemistry that I did not mention, is not lithium ion and is not part of the chemistries, as long as you know exactly how the cell operates. That's the beauty of customization in COMSOL, that COMSOL provides you with generic battery and electrochemistry interfaces that you never get a stock. Even if it's not one of the chemistry that I mentioned, you can easily build a battery model based on your own proprietary chemistry that you have in hand and do the exact simulation and get a sense of how the cell behave and conduct full electrochemical characterization. But hopefully the example that I just review with you is just a set of examples that can be done. All of them are available on our website. You can go and read the full examples. You can have access to the model examples, and you get to see how these studies have been done and maybe inspire you to build a model for your own project. But let's say you have picked your skills, you have picked your frameworks, you have picked your chemistries. At the end of the day, I keep saying this virtual prototype or characterizations, you get the full image here, that you get to apply any type of load profile that you have in actuality to your battery models and see how the cell behaves. Can be as simple as constant current charge and constant current voltage, or CCCV, or power profile, or it can be any characterization profile, known ones like HPPC, rate capability, or on frequency side, EIS, cyclovoltmetry, or it can be any customized load profile, that what we see on the image on top on the right hand side can be drive cycle, or can be a load profile that you already have in hand, and how easy it is to actually import it into COMSOL. Not just that, drive cycle, the other thing that it actually adds to that customizability that I mentioned, anything that you have in terms of material property, in terms of your cell geometry, in terms of the characterization profile, easily can be imported into COMSOL. So you can have the profile, you can have the battery chemistry framework that you have, but you can build upon it and bring in everything that you have outside of COMSOL and get the response of your battery cell model. So that's the thing, that you can customize it as much as you want, but a COMSOL gives you built-in cycling feature that replicates battery cycler that you have in lab, and you can replicate the load profiles that you have when you run the experiment on your batteries. Aging and degradation would be great if the cell wouldn't degrade, but that's one of the main issues with battery. It doesn't matter even if you don't even cycle them, if they're sitting on the shelf, they lose some capacity over time. So battery folks, they are concerned with this degradation in terms of calendar life, in terms of cycle life. If you're cycling them, you want to know how much capacity you're losing. That's the most important thing, but also what it leads to. Is it just capacity? In many cases, capacity loss is not the only issue. They lead to some other issues. Electrode gets deformed, current collector gets dissolved, electrolyte gets completely consumed. So there are some other consequences that you would be interested in. You would like to resolve different degradation mechanism here, as you see on this slide, but not limited to. Most of them, you might relate to them if you work in lithium ion battery, like solid electrolyte interface formation, that it's there no matter what type of formation, no matter what type of profile you apply to your cell, you have SCI formation. Or lithium plating becomes more pronounced when you are charging in high rates or low temperature. Or mechanical degradation, which some of them, they go hand in hand. You have SCI and then you might plate, and when you plate, you have SCI, new SCI on it. Or as a result of plating, you might have dendrite growth, and then it might fall into mechanical degradation. Or electrolyte, the particles might swell as a result of a particle inoculation and deinoculation. Then you have mechanical degradation. You might then simultaneously have gas evolution. You might have corrosion on your current collectors. So that's the complexity of degradation and capacity loss in batteries, that in many cases you're not limited to one. Many of them are taking place. And the beauty of modeling is that you get to capture all of them. Not just that, but you get to capture how they interact with each other, how they intensify each other, get the accumulative effect, but also the consequence of degradation. Not only in terms of capacity loss, but in terms of how the structural and mechanical integrity of your cell gets affected, and so on and so on. And then we get to thermal analysis, which I touched on in the beginning when I was talking about multiphysics, that how batteries by nature are multiphysics. But no matter what chemistry you work on, all the chemistries that I mentioned, you have very good reason to be concerned about temperature, because temperature affects your cell performance and temperature affects cell degradation. In fact, if you do not consider temperature, in many cases, you're making a very simplified assumption here that the temperature doesn't affect your chemistry, which in many cases is not a so good assumption. So no matter what, we're not talking about abuse scenario, I will get to in a minute, but no matter what, in terms of cell operation, how the cell operates, temperature goes high, might trigger some aging degradation, intensify degradation. Temperature goes down, it might actually trigger some other degradations, such as lithium plating. So there is an optimum window that you need to find that the cell operates and performance is optimal and the degradation is optimal. If you work with battery packs, you have a bigger issue, because not only you're interested in capturing temperature on the cell performance, but you're after uniformity. You want to look at the entire battery pack and you want to make sure that the temperature across the battery pack is uniform. You want to avoid having any hot spots, right? And then you get into worst case scenario. If you have a cell lithium ion battery, it's known for it is one of the issues that people are trying to get to next generation batteries. But if temperature passes that threshold, then you have a big problem, because the cell might go under thermal runaway. And then we already know what it has. The temperature spirals out of control and cells start destroying itself and leads to many catastrophic consequences that we want to avoid for obvious reasons. And again, if you have a battery pack, you have a bigger issues, because the thermal runaway doesn't stop with a single cell, propagates throughout the entire battery pack. So by building a thermal runaway model in a battery pack, you want to know, first of all, which cell goes under thermal runaway first, which cell is the next, and the next, the order, and then how much time you get as the entire battery pack goes under thermal runaway, how much heat will be dissipated, and hopefully design a thermal management system that can completely mitigate this. If the cell goes under thermal runaway, you can shut down the problematic cell and maybe you can survive the situation without having any catastrophic results. So battery folks, they're concerned about thermal analysis more when they go on the battery pack, more if they are working with lithium ion batteries. But to be honest, there is no exception. In many cases, you need to consider that, and you have good reasons to consider it. In COMSOL, all the battery interfaces that I already mentioned, automatically they calculate heat generation for you. So you already have access to heat generation that stems from Joule heating, stems from electrochemical reactions or so-called activation, or because of concentration variations or heat of mixing. You get the different contribution and you get the entire heat generation as a total as well. And when you build an electrothermal model, which you can do that across the scales, you can do it on a single cell, as you see on the images on the bottom, or images on top on the package scales. This electrothermal model is automatic in COMSOL. I will show you in a minute, because I'm going to walk you through building an electrothermal model in a minute. But you see, this is automatic. Battery interfaces calculates heat generation. They pass back heat generation to heat transfer. Heat transfer receives that, updates the temperature based on how thermally you have designed your heat transfer model, and pass back the updated temperature to your battery cell. And you don't need to do anything, because this multi-physics coupling is done behind the scene for you. As a result of it, you build an electrothermal model, like for the prismatic cells, you get to see the temperature distribution in it, or in the battery pack that you see on top, you get to see exactly find the hot spots. Again, regardless of worst case scenario, abuse scenario like thermal runaway, or any short circuit that takes place in your cell, you get to see how uniform the cell is operating. And if if your job is designing a thermal management system, how good of a job you're doing in terms of designing a thermal management system. So with what I just covered so far, hopefully you are well familiar with the multi-scale nature of battery modeling, multi-physics approach of modeling, what COMSOL provides you with in terms of built-in physics interfaces that it entail all the underlying theory. And on the underlying theory, you're capturing entire electrochemistry, and you get to couple that with the additional physics. That additional physics can be heat transfer, can be a fluid flow, can be a structural, or can be any other physics that you can think of. You never get stuck, and you can get creative as you want in terms of multiphysics. In the following slides, I want to show you some slides that I will walk you through, and you get to see, first of all, you're looking at COMSOL user interface. If you have not seen COMSOL before, the screenshot that you see on this slide is actually COMSOL user interface. And you have seen a slide before for different application, which is very common that many people these days are getting into battery modeling, but they have used COMSOL back in school or in their other job for other applications. One thing that it's very nice is that no matter what physics you learn COMSOL for, you already know how to use COMSOL for other physics. So if you know how to use COMSOL for other physics, once you get into battery modeling, it's just knowing the battery physics interfaces. The rest of it, you're good to go. So if you have used COMSOL, this serves as a refresher to you. And if you have not, let me walk you through the workflow of COMSOL. You start with the geometry. That geometry can be imported into COMSOL if you have used other CAD softwares, but you can also use COMSOL to build that geometry. You have some material properties that you can leverage material library that COMSOL has for active materials or for other components like the current collectors. But if you have your material properties, again, as I touched on earlier, you can bring up all those measurements into COMSOL and define your own material properties. You get to physics interfaces that you have. Battery, we're looking at a battery interface. You see the setting window. This is how you interact with COMSOL. You put in different, you specify operation mode here, the capacity, state of charge, but that's how user interact with COMSOL and specify different inputs. You take care of customizing different parts of the physics interface you have. And then you might have additional physics. In that case, we are building an electrothermal model. You get to see additional physics here is heat transfer. You see the energy balance. That's what I like about COMSOL, that it's not black box. Although all the equations are defined for you, you know what equations COMSOL are solving for you. In that case, for instance, you know, is energy balance, and you're solving for temperature. And then that was the automatic coupling that I touched on earlier, that these physics are automatically coupled to each other behind the scenes. You don't need to do anything, but COMSOL tells you how it's connecting these physics together. And prior to solving the equation is a finite element tool. That means meshing is required to make the simulation domain ready for solving equations, and discretization, which this mesh sequence is in most cases automated. COMSOL takes care of it for you, but you get to control over it as well. Some users prefer to have more control over it. But either way, when you have your geometry, when you have your material properties, when you have your physics, if it's needed, couple them together, then meshing is ready. You're ready to solve the equations, and COMSOL is actually ready to solve these equations for you. And that's what it does. Behind the scenes, solve all these equations for you, high fidelity, and then will provide you with the results. That in the results and discussion, you get to actually look at different variables. You get to see the temperature profiles. That's what we are looking at actually here. You get to see the, you get to do plotting. You get to plotting different variables, temperature, for instance, voltage of each cells, or voltage variation across the bus bars, or state of charge and temperature profile. Or you get to do different also evaluation, like by evaluation, I mean integration, averaging, knowing where is the maximum and minimum, and all the other things that you will need to in terms of results and discussion. So the slides that I walk you through show you the workflow. That's the workflow that remains consistent no matter what physics you solve for, and no matter what other complexity you add to this model. you can go ahead and add structure analysis to this model. It's a matter of adding another physics interface to it, but the rest of it, the workflow, once you learn it, you know it for all physics, and you get to run your analysis in the same way. So if you go to COMSOL and then try it out on your own, you're going to recognize the physics interface because the graphics user interface, the model builder, everything remains the same regardless of type of analysis that you do. The last thing that I want to leave you guys with before I show you the COMSOL user interface, it's another facet of COMSOL that many people know COMSOL because of this model builder. It's well established in the marketing world that building a model, but there is another facet of COMSOL that maybe many of COMSOL users they might not be familiar with it, and it's building simulation apps. And it's something that we believe that what I covered so far was a discussion for someone who is interested in battery modeling, and wants to build the battery models and hopefully get all the benefits that I just discussed. But what if you want to build a battery model and then share it with people that they're not necessarily battery modelers? They're not familiar with the physics, they're not familiar with COMSOL, but they get to have the benefits of battery modeling. That means they get to do some variations, some changes, for instance, in the design that they have, in the material properties they have, and they rerun the simulation. That's where the idea of application builder and simulation apps come into play. Any COMSOL user can build an app based on the COMSOL model that they have, not specific to a battery modeling, by the way. And they can customize it the way they want. They create their own mini softwares, create whatever inputs they want, whatever outputs they want, and then share it with people that they can actually share it as an executable file that people who get it, they don't need to have COMSOL. They don't need to know COMSOL modeling, and they don't need to know battery modeling. They just get the model, they just get the app, and they rerun simulation and they get all the benefits of simulations because you have designed an app out of the models you have. That's the app that I want to show you, and I want to actually end my simulation, end my presentation with, and it's actually one of the apps that you can find on our website. And we just saw this screenshot of this app on our on my presentation. I walk you through how the model was built, then I discuss how you can actually build an app out of it. But we are looking at the app user interface that someone expert in battery modeling, expert in COMSOL has created this app, and then we are looking at a battery pack battery pack app that can be shared as an executable file. Whoever has designed the app, they can go and change the cell battery pack configuration, how many battery pack they want to put in series. They want to put in parallel, the diameter, the geometric dimension of the batteries, the battery material properties, the operating condition that they want to have. And then whoever gets it, they can just rerun the simulation over and over again. And then in this case, they're looking at the temperature profile, or they can actually have a slide bar, march into time and see what about half an hour later and see how the temperature profile changes as well. So they're interacting with something that they've not been involved in the modeling process of it. You can find this app on our web, and everything that you see on this app has been designed, how the report can be generated, what plots can be shared, or what inputs you provide. You can actually do parameter estimation on the cell level, for instance. You can ask the user of your app to share the some inputs, experimental data, and perform parameter estimation for it. So this is the facet that whoever gets the app interact with, but I'm gonna take different layers and take you to the model builder and tie it back to the discussion that I started with. The model builder, the battery pack designer actually app, then this is the application builder. This is the behind the scenes that whoever was the battery modeler design a battery app based on the battery models they have, and they define the inputs here that we saw in the interface of the app here, what inputs they want to have, what outputs they want to have. They have already designed this, and they have created an app and package it and share it with the user. And if you go one layer down, we go to the model builder here. This is where the model was built. You see the battery model, you see the heat transfer model, and we already saw in this screenshot exactly on the model builder how this model was built. So you see how we can go from model builder, which battery expert can build a battery pack model by resolving the physics that we saw on the slide. They can go to the application builder and build an app out of it. And they can actually, once they do the testing of the battery, they created a mini softwares that can be shared with people that they don't know anything about COMSOL and they don't know anything about battery modeling. This app and also all these screenshots that I showed you, they're available on our website. So feel free to check them out. You can download these apps and play around with them. They're very cool. And so far, you heard from me all the model examples that we have on our website. We have modeled different scenarios for lithium-ion batteries, different chemistries that you can go and check them out. But not limited to that. It's always nice to hear from our users. And what we're looking at is that one of our users, IAV, that they're designing a different battery packs and they are integrating different chemistries, not just sodium ion, solid state, and LFP, and taking advantage of all the good things of each chemistry. So they have a battery pack that has 3 chemistries, and they can toggle between different chemistries, different mode of operations. And you can see on the right, they have actually built an app out of it. So they share it with their users. The users can play around with thermal modeling strategy or what chemistry they want to activate or not activate and all the cool things that they enable users to play around with that application that they have shared with their users. There are plenty of model examples. There are plenty of learning materials and blogs that you can find on our website. So if whatever I said, I try to give you a glimpse of what can be found on our website and what can be explored. I highly recommend that you go to our website and see similar stories, read the stories from our users, review the model examples that we have already on our material, learning materials, blogs that we have, training courses, and etc. and etc. There are a lot of things to be explored. I really hope this was helpful. I really hope that this gave you an overview of what can be done in COMSOL. I try to cover different facets and some fundamentals, but I'm also aware that all of you guys, although I try to cover all typical modeling scenario, many of you guys might be working on some modeling scenarios that I did not cover, or a chemistry that I did not cover, or you might have some specific questions for the modeling project that you have at hand. I highly recommend that you get in touch with my colleague Ian, that you find his contact info here. First of all, you get to get a free trial of software. If you have not tried out a COMSOL, I highly recommend do it. Give it a shot and see, get to use all the features and capabilities. You can definitely contact Ian and ask for a trial. But also, if you want to discuss your modeling project in a private meeting with engineers specialized in battery modeling from our engineering team that I'm proud to be part of, then we can definitely arrange a meeting and we can sit down and discuss and brainstorm and discuss your particular project more elaborately as well. Thank you so much for attending. I really appreciate that. And I really hope I get to stay in touch with you and discuss your modeling project more in detail. With that, Michael, we can now open it up to any questions attendees have.
Fantastic. Thank you for the information, Nilfar.
Of
I
course.
see we have quite a lot of people very interested in the work here. Before we start, 2 things. First, if you have questions, please do enter them into the Q&A feature of Zoom and not the general chat, as we'll be answering Q&A from the Q&A feature. Second, I'm going to turn on a document that Nilfar and the COMSOL team has provided. This is a PDF that you'll be able to download for the COMSOL Multiphysics work that Nilfar just went over. All right, let's get started with some questions here.
Sure.
Maynard is opening up the floor with the first question. Nilofar, in your experience, what are the most overlooked physical couplings, whether it be electrochemical, thermal, or structural in battery systems, and how does COMSOL help highlight them in early design?
I believe one of the most neglected one is electrothermal model because many chemistries, other than special lithium ion, some people assume that the temperature dependency is negligible, but in many cases it's not, especially if you're after degradation. Degradation has a strong dependency on temperature. I've seen that some people they go with isothermal assumption, which is not so good
Mm,
of assumption. The other thing is structural aspects that more and more is getting attention. More and more people they have tried to understand that this, especially lithium ion based and intercalation based chemistries, that they go under, especially if it's not graphite, they go under considerable swelling, and that swelling can be affecting the electrochemical performance. And how COMSO enables that is that again, as I mentioned in my presentation, you get to have different physics and you get to talk to each other based on how you become in charge of defining how these two are coupled. More and more papers are being published that how electrochemistry structural, for instance, are affecting each other. If you know the theory, if you know, you get to exactly make these two interfaces talk to each other the way that you want. So you're not stuck with one theory, one approach. And especially with more and more coupling strategy and theory are being introduced in the literature, COMSO enables you to do as much as customization you want in terms of multiphysics. Hope that answers your
fantastic.
question.
A lot of flexibility, it sounds like, in this platform.
Yeah.
Awesome. Info is asking the next question. What is the computational effort requirement for a console? And additionally, does it generate material property data for different components?
Well, there is a, let me start with the second question, then I get to the first one. There is a material library for common lithium ion materials and some other chemistries that could be very good starting points, and you can definitely use those materials. But, and based on my experience, many users, they prefer to have their own material properties. They bring them into COMSOL, which will be fully confidential, and then you will have, you will continue use them as a part of your own material library. So there is a material library, but definitely can be extended by your own material property. And back to the other question, that computational cause, many factors go into it. It's a matter of the physics. Back to the slide that I mentioned, you want to go with high fidelity models or simpler models in terms of theory, but also do you want to consider multi-physics or do you want to, in many cases, for instance, for lithium ion battery, 1D geometry suffices if you want to do high fidelity. But let's say your objective is tap design. You want to for sure go with a 3D geometry. All of these aspects can add to the computational cost. But one thing that I want to mention is hard to estimate it beforehand. It's very case dependent. It really depends on the aspects that you decide. But in many cases, regular machines, I've been using COMSOL on a regular machine that suffices in terms of computational cost. But just letting you know that you can also run COMSOL on cluster if that interests you. And if you would like to leverage the benefits, that could also be done.
Gotcha. Okay, thank you.
Of course.
Kevin asks, is it possible to learn how to use console software?
Yes,
Like,
we
what would you
have a lot.
recommend?
We're actually on a perfect slide because as for the learning material we have on our website, we have a learning center that you can go, and there are so many articles that forget about battery modeling. I get to battery modeling in a minute, but let's say you want to learn COMSOL in general. There are so many free materials that we have in terms of articles, in terms of videos, in terms of webinars or archive webinars that show you exactly how you can set up a models. There are a lot of model examples that I mentioned. They come with step-by-step modeling instructions, and they are perfect self-training resources if you want to learn COMSOL. But also we have paid training courses as well, both for introduction to COMSOL, but also battery modeling or application-based areas. For instance, battery modeling course is coming up in January. There will be a course in January focused on battery modeling. So there are a lot of resources that you can explore on our website, and also you can find training courses information on our website as well.
Awesome. Thomas asks, first, thank you for your presentation. And second, he asks, concerning mechanical degradation, can we apply external pressure fields on the cell? And if so, can it be non-uniform or customized?
Yeah, definitely. That's something that you do under solid mechanics customization. So you have battery interface and you have solid mechanics interface. Under solid mechanics interface, you define how the cell or pack structurally interacts with the environment. And part of that interaction is the pressure, which in case of pouch cell is actually you might intentionally apply pressure. And that pressure can be in terms of force, can be in terms of, well, whatever units you have, can be a constant, can be time dependent, and can be space dependent. Whatever condition you have, definitely as a boundary load or domain loads can be applied to yourself. And once it sits in the solid mechanics, as long as solid mechanics is coupled to battery interface, automatically your motor captures that. So the answer is yes.
Awesome. Thank you. Uh, John asks, also thank you for your presentation. But for best developers, can we model commercial solutions for utility scale applications to get degradation curves for a time series cycle?
Michael, the first part. Can they develop commercial?
Solutions for utility scale applications. So essentially, would you be able to model the entire best system to get degradation curves?
Yeah, definitely. It's something that back to that scale thing. It's something that first of all with degradation comes again customizability. It can be any form of degradation that you want, and you get to implement degradation on different scales. You can go all the way on just degradation on the electrode, on the cell, on the group of cells, and go all the way up. And you get to have that complexity control over it as well. You get to resolve exactly how degradation takes place. Is it like, for instance, SCI plating? Or in a holistic way, empirical way, that I just know that on my entire large system, this much degradation is taking place and this much capacity I'm losing. The nice thing is that the control that you have over complexity, you can go with a full resolution or you can go with a simplistic way.
Hmm. I can imagine that'd be very useful for either battery engineers or asset developers. So
Exactly, yeah.
it's yeah, there's a wide range. Well, we are at the top of the hour. I know we have quite a lot of questions left. Please, if you have more questions, you'd like to inquire more, Ian Wood's email is on the screen. Please do reach out to the console team. They'll be very happy to help you. Just want to give a quick thank you for Niloofar for the presentation and the
Of
wonderful
course.
insights that she's going to provide, and also for everyone who's attended today. Um, Really, it's great to see this much engagement with our programs, with COMSOL, and with the battery community in general. And we're looking forward to seeing you at the next event. So thank you, everybody, and thank you, Niloofar.
Thank you, everyone. Bye.